already. I figured start a minute or two earlier and go ahead and kind of get started with all of this. Like I said, hello and welcome. Glad to see everybody nice and peppy at the end of all this. So 2-3 days. So hopefully everybody will find this engaging and informative on it. Today we're going to be talking about the U.S. Army Corps of Engineers, how we enhance commerce, national security through data-driven geospatial insights. My name is Jeff Moroz. I am a contractor for the Army Corps through a company called Woolpert, where I'm a technical lead for a geospatial company, and we work directly with the Mobile District, the spatial data branch out of Mobile, Alabama. In case you guys don't know, the U.S. Army Corps of Engineers has been around for a very long time, and they have a very unique mission that is very much nationwide. It's to deliver vital engineering solutions in collaboration with partners to secure a nation, energize the economy, and reduce disaster risk. It's kind of a bit of a mouthful, and it incorporates a lot of different things. We're going to be kind of very much a little bit more narrow focused in terms of talking about what they do on the civil works side and what they do for waterways. They engineer solutions that really kind of tackle challenges on a national level, which is very unique. The USACE Civil Works staff oversee construction, operation, maintenance, all the dams, canals, flood protection zones in the United States, as well as a wide range of public works all over the world. Guam, they help out and give expertise in different theaters, different countries, and have teams all over the world. There's approximately about 37,000 civilians, and I don't know the number, but a lot of contractors that also help and encourage. They work directly with industry in a lot of cases, helping them kind of map out, contract out, and really kind of attack and help maintain the nation's infrastructure. Today, we're really going to be kind of looking at the federal navigation system. I know a lot, if you've ever been on a boat, if you've ever been an intracoastal waterway, I see everybody got your cell phones, everything like that. Commerce, industry, large vessels, container ships, it all uses our national waterways, and maintaining those is extremely important for national defense as well as maintaining our economy. The USACE navigation system is responsible for maintaining and improving about 12,000 miles of short draft, so 9-foot to 14-foot shallow inland waterways, and about 13,000 miles of deep draft, anything more than 14 feet in total. 400 ports, harbors, and turning basins throughout the United States. They're essential. They're essential for how we do business. They're essential for strategic reasons and just getting basic goods and services out to people. If you all can recall during COVID when everything shut down and ports and harbors just weren't working and everything just kind of slowed down to a halt and stuff, their job is to maintain this and keep this moving in an efficient way. It's a nationwide effort. There's approximately $2 trillion of commerce annually moved through our waterways. That's more than 48% of consumer goods bought by Americans pass through USACE-maintained harbors. Big job, important job. Over about 1.5 billion short tons of freight moved through U.S. ports and waterways just in 2020 alone. And then 743 million short tons of domestic goods. And 15% of domestic freight is carried by water. So a huge portion of our just domestic goods and services getting to ports and getting to actual end users at the end. To couple with that is the challenge of actually maintaining it, and that's through the dredging process. It incorporates about a budget of about $1.5 billion a year, and about $2.5 billion a year was the cost to actually remove all the different material from the channels, and that's an each and every year process. So it's constantly moving. They're constantly dealing with these natural processes and these dynamic systems that are always on the move to do that. With that comes various different types of dredging that happen within that. About 77.5%, that's just maintaining dredges and existing channels that exist right now that are there. So they're constantly getting, as soon as you dredge them out, they're constantly getting refilled with material every single day. As the tides come in, water comes in, all kinds of different ways. You got 13.2% comes from different types of new construction, so with different types of vessels. Different areas require different draft depths. So you have a particular channel that have been historically dredged at one particular level, and it has to be lowered, so that requires more effort to remove much more material in going that way. And then 83% of this is actually done by private industry, with the remaining done by the USACE operated fleet. Here's a good example. This is taking some AIS data of traffic just for the year 2021. It's just how much traffic that we're talking about. Like I said, these are nationwide problems. These are nationwide challenges that you deal with on a very much a yearly basis, is constantly churning, constantly in motion, constantly needing to be improved. And with that comes the need for data-driven decisions, real-world data-driven decisions. We talk a lot about a lot of the sexy, really cool things with AI, ML, all that stuff in there. This is kind of boring stuff, but it's also foundational for how our society operates. When we have data online, it will be great for humanity, and it is a prerequisite to solving many problems that humankind faces. Where that becomes important is, how do we take, with finite funding, time, resources, how do we make critical decisions within this dynamic world? How do we understand it? How do we decide what types of information we want to get? Because there is a bit of an information economy. What is important data, what is not? And how do you kind of sift through making and doing that? In comes in is the National Dredging Quality Management Program. The National DQM Program is tasked with providing USACE to nationally standardized remote monitoring and documentation systems across the multiple different types of industries and vessel types with timely data access, reporting, dredge certifications, data quality controls, and then data management. It's a lot of data, and it's a lot of different types of data. So the constant process of doing that. You may or not have heard a lot of conversation about this people, process, and then technology. This is where we're talking about the people. These are the people that are every day kind of churning in and have created a culture to kind of take this data in, manage it, make sure it's the best quality that they can, and then push it through, and then make sure it gets to decision makers downstream. And as you can see here, it's also developed cost-effective and state-of-the-art suite of tools and products that provide transparency to USACE dredging operations while building relationships with industry and then also with the local communities. This is also very much a local effort. They collect information, it goes down to the local dredge operators in various different districts all over the country, who then are empowered with the data to make critical decisions in their particular domain. What is DQM? So DQM largely is a USACE dredging industry partnership. It does not exist without our partners in the industry. To make it happen and to manage it correctly and efficiently takes that kind of cooperation with them. It also means that there's near real-time automated dredging monitoring system. So they're out there right now operating, sending us data back, informing us what's happening with the independent dredges on a vessel level, all over the country, and in some cases all over the world. Standardizes dredging monitoring requirements. Standardization is important, understanding what pieces of information are critical to making decisions and which ones aren't. Provide performance-based instrumentation requirements. With each contract that gets passed through, we standardize requirements. What's the instrumentations? What are the expectations to set so that we can measure how fully a contract or a particular project was completed. And then serving as a repository for historical dredging operations. Where that comes into is understanding historic trends, understanding our trends changing, how things are functioning and moving in the dynamic world as we proceed through time. And then deliver tools to review, analyze dredging operations. If there's a particular project that's happening, are they living up and meeting expectations? Which has real world and cost factors associated with it. DQM and OTIS, the project began as an R&D project called Silent Inspector in 2001. DQM has evolved to become a data source of truth in the US dredging industry. And it encapsulates USACE civil works, government and private dredging operations, and tracks impacts of dredging operations on endangered species through its companion program, the Operational Dredging and Endangered Species System, we also refer to as OTIS. That has to do with a lot of sea turtles, whales. They all exist within this ecosystem that we're trying to pull material out of, and they get affected by it. So we also have a secondary system that helps us track that impact on those species. that has to do with, per the Endangered Species Act, we have to on a regulatory level. So it's not coming in, kind of destroying what it is, that all gets built into the calculation and the decision making. There we go. So with this also comes, this is an evolution that started in 2001, but really kind of got kick-started around 2011. And with that too, we also have several other systems that have attempted kind of historically to do that. So all of these systems starting in the 1960s with the DIS system, the Dredging Information System, and then kind of moving into the RSM management system, which are very manual processes. They do similar but different things and contain different types of information. And then finally, the DQM program, which is now the kind of technologically emergent data source of truth for the dredging industry. In real time, what does that mean? So DQM is currently receiving data from 20 different hopper dredges. So hopper dredges are these large vessels that, almost like a dump truck, where they take material out, drop it into that, and then they go and dump it somewhere else in a defined particular area. Scows are very similar. They're more kind of these, they're not connected to it, but they get dropped into that. And then pipelines, which have essentially, you drop a big hose in like a vacuum and start going back and forth to kind of pull that material out of that. With that, that's about 2,000 contracts and permits that they work to across 34 different districts and 7 divisions within the USACE operations. So what types of data are we talking about? What types of instrumentation? A lot of it's telemetry data. It's lat-long GPS, course, heading, speed, suction, head position. You have drag, suction, head depth, slurry velocity, fore-aft displacement, fore and aft ullage, so it's total volume, as well as different types of hull statuses. So there's lots of different information that has to do with it, which is very specific towards vessel types. So which means that we can't just grab all the data. It comes from various different types of vessels, and which requires different types of analysis to do that. So it requires us to have a system in which we can take each of them independently and analyze them for the various different swim lanes that they operate within. And here's just a very simple example of the DQM data acquisition pathway. We take vessels that are always constantly sending us data. Some of them either satellite or however way we do it. We have a mix of streaming data that's kind of always coming in, something that's in near shore and they have a connection to do that, then they send it. If they get away, it'll buffer, and then as soon as they get within a range, it'll try to send it out, but it gets to the transmission, then it gets processed, stored, and then we have a viewer that's attached to it so that our industry partners and decision makers can review the information that's coming in and making the critical decisions they need to. Data available, plant location, that's kind of our terminology for what a dredging vessel would be, and then various different types of indicators of types of activity. For us, in a lot of cases, we have a mixture of kind of deterministic and then probabilistic data. In terms of what that dredge state is, kind of depends. We get where it's at, its lat long, and some of the sensor data in it, but we use that to piece together and run analysis on it to get this kind of determination of what exactly it's doing in that real-time aspect of things. In some cases, right now, the existing system, we're about 10 to 15 minutes, and that depends on that to do that, but with our next migration that we're working on that's in process and modernizing, we're hoping to seal that gap to be almost real time. And we'll cover that in a little bit. With that too also comes what I kind of just described is like the idea of a cycle, is the fact that as we kind of dredging operations going that, there's several aspects of it that we need to determine kind of what is a cycle. So a dredging cycle incorporates a unit called a cycle to represent the progression of dredging operations on a particular project. The events within that follow into a progression, like an undetermined, we don't know what it is. It's sailing light, which means it has no material on it. It's dredging or loading at the time. It's turning, it's sailing loaded, or it's disposing. So it gives us this complete picture of not just where the vessel is and a whole bunch of telemetry data on things, but also it helps us paint a story in terms of like, as this progresses, where is it going, how is it doing it, what is it doing, so we get that complete picture of it in real time. And with this too, DQM is just one kind of piece of all this puzzle. We take data from, to make the critical decisions too, there's also the idea of DQM covers it while the dredges are operating to do that. But to do that, we also have to know, we have to have various different bathymetry surveys that go into it to determine how much dredging is required, how much material is there to be moved. The DQM program will be run, a project will be run, and at the end of it, there's an after dredging survey to determine kind of what the progress is. Did they actually complete what they needed to, and then where is the next current state of that? With that, it's almost like, if you look at the data kind of a long term, it's almost like a heartbeat. You have these various events that happen, pulls the material out, and then it builds back up. And it's this constant flow, almost like it takes on a life of its own within the waterways that we deal with. So, like I said, we talked about our people, the DQM people, our process, what we need to do to collect it. Now we're kind of getting into the technology about it, and that's kind of why we're here today. DQM version 1 stack is an operational system currently on a hybrid system. We operate both in the cloud and an on-prem system. We use the IoT cloud infrastructure. That's how we get our streaming data in from the field, and then event-grid topics to consume the data on-premise through various different listener services. The system then reaches out to the cloud from on-prem and pulls the data down to then get processed within an Oracle database, and then it's analyzed and processed. Like I said, this is the system from about 12 years ago. So it's that older kind of on-prem system. Within that too, we have VMs that run MATLAB applications that are constantly reading and analyzing the central database and then giving us results. That's why I talked about that kind of probabilistic. It runs through, does a bunch of calculations to determine various different types of aggregated data sets that then get analyzed and reported back. So really why we're here today is with that migration is the migration from V to the cloud. The conversion to the cloud is the current phase of the DQM. Migrating an on-prem system to the cloud presents some unique challenges not seen within cloud-native applications. If anyone's ever tried to modernize something, it's a lot more complicated if you have to move something up that's already existing into the cloud versus starting out fresh. And then after examining current and future needs, DQM codes the Lakehouse architecture as its tech stack to meet those modernization needs. On top of the complications with just modernizing legacy systems, you also have the added thing of it being a government system, which comes with its own kind of set of unique challenges to deal with. Modernizing government programs and applications to cloud environments offers very different challenges from those that are just cloud native. We have to deal with lengthy approval processes, security considerations, and slow feature releases affect the progress and pace to effectively manage these technical debts. In a lot of cases, we don't get to play with the new happy, shiny objects. We have to wait probably anywhere from 6 months to 2 years sometimes to get some of it. So with that comes, we still have to make progress. We still have to move forward with that. Managing operational and development systems in parallel creates additional workloads to manage and migrate to. Like I said, with a finite amount of money, finite amount of resources, we still have to maintain the version 1 and execute on it while we're also building these up in the cloud. So the limitations in which we're dealing with that kind of prompted that migration to the cloud are the system is difficult to scale. As you know, with all scale, an on-prem system requires the purchasing the products and the various different hardware, software, and applications and middleware that does it, and that's a pain to be able to do. With on-premises infrastructure, we're responsible for all of the updates, security patches, which requires additional time and resources. Data sharing is cumbersome in its current state. We operate within a very tightly controlled government network, and that comes with a lot of caveats to it. With a hybrid system, it's not possible to leverage the new tools for analysis enrichment. There's a lot of things that are doing amazing tools to do out there, but if we can't get the data to them and we can't use those to analyze, they're kind of useless to us. And then finding people to manage and develop legacy systems gets more challenging over time. Oracle, some of the other older legacy systems, like I said, people are not coming out. It's harder and harder to find people to work on these systems, so we have to move where the people are and where the skill sets are. The system is segmented into interrelated data systems and connectors. So that kind of creates a little bit of a morass to try to organize to how to connect things in an efficient open source way. And then changing and adapting schemas and data shapes is difficult. So as data comes in, as we want to migrate, as we want to change, add on new vessel types, it just, over time, it gets more and more difficult to do that. So the reasons and considerations for the migrations to the cloud are kind of fourfold, is enhancing the scalability and resource flexibility. We're moving our on-prem GIS data systems to the cloud will allow us to seamlessly scale our resources up and down based on demand, enabling us to handle large data sets and complex spatial computations efficiently without investing in new hardware. Like I said, we want to try to leverage this as much as we can, but it also opens up opportunities. Is if we don't have to manage some of the hardware and some of the other aspects of things, that frees up bandwidth for our people to really start to think about what are the better ways in which we can mine the data, enrich the data, and come up with better decisions and better answers. Cost optimization and reduce infrastructure burden. Simplification. Smart, simple, everything we can do to simplify and change our footprint to be as simple as possible, we often view as the ideal situation going forward. Accelerated geospatial analytics. Databricks provides a highly parallelized and distributed computing environment, enabling faster processing and analysis of GIS data. This empowers us to perform complex spatial analytics, machine learning tasks, and unlocking valuable insights for geospatial data in a fraction of the time. For us to do some of the analytics that we're doing, it goes from a matter of, let's say, taking an entire data process to sometimes inside of 15 to 20 minutes. With the power to do that, you can then get really creative with how you can run your analysis, run your reporting, and really aggregate your data in very extremely unique ways. And then the ecosystems for integration and advanced analytical capabilities. Our ability to touch different types of data stores, to connectors, all of that just enables us and gives us opportunities for emergent abilities we don't even know or really haven't begun to really kind of tap into. Like I said, with this too comes a kind of, not so much a technological view on things, but also us really kind of flipping kind of how we view some of our processes going well. Some of you may have seen this. This actually comes from Databricks, is that whole ETL to ELT kind of swap is data on read versus data on write. And with that comes some changes in terms of how you want to approach it with your pipelining, with your data ingestion, and then kind of with some of your downstream tools as well. With all those considerations, we chose Databricks Lakehouse as the architecture of choice moving forward. We weighed several different options, but the more we looked into it, Databricks provided the structure and the capabilities that we needed to really to move this into the future. This is an example of our V2 architecture on the Data Lakehouse architecture. It's a next generation architecture that will enable us to unlock the true potential of our data. It's compared to what it was before, this is extremely simple. It's very straightforward. And now we can have people actually focus on the data versus focusing on the complications that have to do with the architecture around it. I'll sit on that for a moment. I see some. So with that comes, like I said, we have the challenges that we have with the version 1 stack, but that's not to say they're not going to be our own complications we have with actually modernizing. Getting data up to the new system required a system of ingest data from on-premise. A lot of ports blocked, a lot of other issues, so we had to work around mitigating how do we get the data up to the cloud. Once we had the data in the cloud, then we had to coalesce it to where to store the data, and we chose the data lake as a raw storage of historic data and wrote a whole bunch of Databricks notebooks to alter the shape of the data to work with our new V2 shape and processes. The cloud itself also presents issues with feature parity from the commercial to the government cloud. I don't know if any of you worked in the public space, but a lot of times they're behind in terms of what they operate to do that. So there's a few people I'm going to try to poke at after this meeting about hoping to make that thing, but it is what it is, so we try to move forward and mitigate from there. Databricks is used to capture and enrich the data into the data lake, but until the last few months, a viable method to build APIs has been a bit of a challenge. So what have we had to do? We've had to do a series of half measures until stuff becomes available, and then we transfer over in that, because again, we still need to make progress. We still have directives and objectives we need to get to. We spent a lot of time trying to find temporary workarounds to be replaced by later features released. We don't have access to an Azure cloud. Again, that half measure things, and that's just the complication that you have when you're starting out like that, or modernizing from an older system. Kind of a second page, kind of moving into it. This being new to technology too, it also requires retraining of people. You have certain idiosyncrasies, getting people trained up and understanding kind of what is Databricks. You could have traditional DBAs, which have done Oracle, SQL, and understand certain types of language, but now they have to move into this Jupyter Notebooks way of doing things, which is vastly different than how they've done before. So it's how do we train our people up there to really kind of understand the nomenclature that has to do with it, with Databricks. There's a word salad. If anybody comes to these type of meetings, it's always interesting if you get someone outside, because to them it sounds like alien language. And to a lot of other people who have been on traditional ones, it's the same thing. So there's that process of branching them and moving them over. Building APIs for data egress has been very much a challenge. It can be difficult to build APIs for tables, so we have to build an API. We built an API automation workflow. We essentially had to build something similar to our own version of Databricks SQL that can be adapted, because with this process, schema changes, modifying, that can be very rapid, so that creates a whole bunch of very quick technical debt if you don't know how to automate that process to rebuild your APIs as the shape and the data changes. And without, let's just say, some of the features that we have within commercial, that puts us in a bit of a jam. So what we did is we created automations to be able to automate the whole process and deploy. A new system also means cleaning out old unused structures and concepts. Whenever you're actually doing the migration, there's always this tendency to want to just kind of that lift and shift mentality. But with kind of that retooling of the whole system and kind of pulling it apart, you can't really do that. But it's also not exactly performant. You have to denormalize things. Everything with some of the legacy system has been so normalized to just get every little bit of optimization out of it possible, but when you push it up to the cloud, it doesn't make a whole lot of sense. So what you have to do is, sometimes without a whole lot of documentation for it, is unpack that and redo it in a way that makes sense. But that also means that you have to change it, and then making sure that we're doing that in a correct way, but also make sure that we can get the same results we did with the version 1. To facilitate the migration, data has to be flattened where possible, which changes the shape of downstream services and complicates the processes to merge legacy data. So on top of us changing it for the version 2 as it's coming in, we also have to have these other kind of migration and merging changes as well to make sure it matches up and we can get it to talk to each other. And then it also requires extra rigor in understanding how to secure the new system in accordance with Defense Information Systems Agency, DISA. A lot of it's emergent technology where there's a lot of, there's NIST information, other things like that, but in a lot of cases it's new technology, so the guidance isn't exactly there all the time. So we have to work with our partners, work with anyone we can to make sure that we're making those correct decisions to make sure that it's as secure as we can get it. So by the numbers, in terms of what we're doing right now, we're running about 21 active Databricks jobs, pretty much 24/7. The 78% file reduction, if you take it from our existing system and put it into the more compressed like Parquet and Avro files, we get almost an 80% file reduction, which is significant if you're trying to store it and for cost-wise. We're also going from somewhere around 10-ish minutes to now being able to process from time of capture of a data thing to gold and being completely processed within under a minute. We're actually waiting for data to come to us now. Where it's more limited by IoT Hub and Event Hub is just having enough data to efficiently do that in a meaningful way, so it's waiting. We also have a whole bunch of data factory processes that come and help us sync up from our metadata and our meta information. So we have our on-prem systems that need to match with that. So we have them coming up from on below, and then we have it coming down, and we have to merge it at some point where that comes together. We have about 600,000 average number of points we get from data a day. Every vessel submits a data point every 6 seconds. So that's constantly streaming, constantly churning. And then our total within our data stores in terms of the total number of kind of AIS records of various different types. Some of it's dredging, some of it's just traffic and ship traffic. It's somewhere in the order of about 10.5 billion. So it's big data. And then how big, just a little snapshot in terms of what our goal tables are, the various different, right now we have about 3 different types of vessels, hoppers, scows, and pipelines. We'll be adding more they're all kind of very quickly kind of approaching billion points themselves. And that grows by the day. We keep adding more and more and getting them on there. And then we're also about to add a couple of different swim lanes for different types of vessel types. As you see, this is kind of just a zoomed in example of what we were talking about with the Internet of Things. How we kind of use the networking and use Kafka, it's Apache Kafka under the surface to route our data in, segment it as much as we can so we can do the various different analysis that differentiates one from the other. In previous iterations of it, it all came in as one, converged into one, and we had to fan it out from there. This time we're actually splitting it out right at as soon as it comes in. And then we're also using the structured streaming. So the autoloader, I don't know if you guys have ever seen kind of documentation on it. That's kind of the magic beans behind all of this that really kind of powers it and makes sure that it works the way we need to. Another aspect that we've also kind of very much kind of embraced is the medallion architecture that exists within Databricks. So within our streaming process, we stick to that very stereotypical bronze, silver, gold processing, and at each level, we kind of do various different aspects of it. Our initial one is where we have our autoloader, our identity, where we append our identity columns to that to kind of keep it kind of a little bit more traditional to match up with some of our older data. And then that's also where we do our boundary checks. The process of getting data, even though it's coming from sensors, can be a little fickle at times. There's human error aspects of things. Sometimes you get data that's streaming in that's absent of a lot of the data that you really need to make it work. So you need to be able to check that before it gets into it and starts to muddle things up and affect the quality of the data. You also have to, at some point, actually start to do joins. So you have to join with other types of bits of data that exist in other database, other tables to do that. So we use that kind of silver aspect to do that. And then those are all appending. So those essentially just a big vacuum, all the data just comes in and goes. And then gold, that's where we're kind of really starting to make the magic happen. We start to really kind of dig into the payload and the body of the messages that are coming in and really start to process it and do it. We have a very unique and difficult deduplication on that in the aspect of we cannot delete records. We have to maintain and capture everything. So with ours, even if it comes into the system, we get resubmittals, we get all these other types of things in there that have to go with maintaining that quality on it. We cannot just throw points away. We can't throw data away, which requires this whole process of essentially coming in and marking anything that might come in as either a duplicate or anything like that. And we do that through a series of, we hash them out, create signatures for each point that comes in and do some of the comparisons that way. But it also requires this very complicated lookup that you actually have to go and traverse all your data to do that. That's created some problems because once you start to get into partitioning, you're competing reading and writes and other stuff like that. So there's been we got a wealth of kind of on-the-job training in terms of how partitioning, how clustering, how all that really needs to work to make sure it plays together. That's also where we do our geospatial analysis. We point and polygon. Is it in the channel? Is it in a disposal area? Is it in a placement area? And the various different aspects of things that we need on a physical place of determining where it is in that particular point in time and what it's doing. Becoming kind of spatially aware. After that, we get into gold, then we dump it into our data store, and then it's very simple from there. We have a series of functions that run our APIs, serve it through a gateway, and then from there it gets served out to all of our downstream applications. Again, I talked to you about the kind of the for each batch, why we have that very difficult kind of use case as it hits gold to where we can't just drop it in there. We have a couple of very different kind of use cases that we have by leveraging the kind of micro batch sessions that we have. So that's much more of a learned pattern that we've really started to work on. We From that, we get real-time vessel positioning updates, so we're able to actually update it pretty much within that minute, so we can actually get real-time. So if some of our managers, some of our people at headquarters want to know exactly where something is, we can provide that to them. We've also started doing something that is emergent within spatial. Within spatial is using H3 resolutions, so H3 bins and hexing. We do point and polygon analysis, the resubmittal and deduplication process, which is a little bit more complicated. And then we also, within that, go ahead and batch order a bunch of optimization and Z-ordering with it while we're at it. So we don't have to constantly shut our jobs down or compete with other jobs on it. So while it's always churning, we're always trying to optimize and try to do it. So the success stories that we've been able to have is we've successfully created medallion level streaming pipelines for all 3 of our vessel types, with the adoption of Lakehouse Architecture and Delta tables, changing the initial system design, removing a traditional data warehouse. The removal of traditional data systems is a big step in evolving DQM into a true big data platform. With a lot of people, remember a few years ago when they're kind of pie in the sky ideas, and I was like, they're like, what do you want to do? I was like, I want to get rid of the database. And they all looked at me like I was crazy. We also built a builder, like I said, the whole idea of rapidly building these APIs, because we need to be able, once we have those upstream changes, we need to make sure it's reflected within the downstream changes. And automation is really the only way in which you can actually really kind of do it. The other aspect about it is with the cloud, the uptick cycle and the technical debt, you can't wait as long to update your code, update your versions, all that. So we need to be able to build a process to where we automate that as much as possible. We also built a library of Python and UDF functions to emulate a lot of the old version 1 capabilities and procedures. The other aspect that we have to do, and we're in the process of kind of finalizing doing, is that comparative analysis. Are we getting the same data from the version 1 that we are from 2? So you get that, move to the cloud, moderate, everything like that, but there's still an expectation of quality, and the expectation is, are you getting the right results to it? Are you not getting hallucinations? Are you not getting all these other data problems that you're going to get by moving to a thing? Because, again, you're coming at it from you're trying to emulate what somebody else did with different set of assumptions, different set of different stack, and different just everything altogether. And then when fully functioning, the system gets messages in less than a minute from the time of capture to complete process into the gold tables. For us, that's a success. This is just an example, I think, of just kind of some of the V2 APIs and everything moving forward. So DQM products and deliverables. Like I said, we got into the tech about it. This really kind of gets into is that with the adoption of the platform, we've also been able to kind of encapsulate a bunch of other types of functionality in there that may have done in various different other ways, and to automate it as well. We do data gap summaries. So as we get from different vessels, the lineage of the data, there's going to be gaps in terms of where, as data comes in, it may have dropped off a signal. You may have said something, or they just didn't submit all the data in what you needed, so you're going to get these gaps. So how do we analyze it and run that in an effective way, as well as the alerting and notification behind it? Generation of vessel and project certification documents, we've automated that. We have now some summary statistics where we can automate that and get some of those certification, those documents out there to do that. So that frees up actual humans to do their jobs better, to really look into the data and really do it with some stuff that is very kind of manual processes. New types and combinations of summary statistics. Geoanalytic tasks, so we can now play with the data in ways we hadn't been able to before. Machine learning for the cycle state analysis. We're currently in the process of training up some machine learning models to determine that cycle state. How close are we now versus the MATLAB and the other types of things in there? We're very much, it's a whole bunch of if-else functions and kind of learned information, but we're trying to now mine that. Is there ways we could speed that up and maybe get some different types of insights out of it? Alerting and data quality checks. That's now the thing that we're going to start digging into is what is the quality of our data? How do we score it? And then for training in the future, different types of models set up in the future, but also we might get things to where, let's say 20 to 50% of the data is good, the rest is bad, but it's not necessarily bad data. It could be used in various different ways. So finding a way to score the data and to segment the data in ways to where some of it might be useful in other aspects, some of it not others. So how do we dig into that and really start to get those insights out of that and come up with a clear, coherent way that some of our analysts and stuff can really understand and start to work with. And then streamlining the processing and submission of resubmittal data. Now that we have within that, it was very much a very hand-jam type of process to be able to resubmit data. It required taking a file, loading it in, pushing it through a SQL data. It was just very inefficient. Now we're working on ways in which we can automate that. Upload a file, it runs it, pushes it in, and we're good to go. Just again, an example of what I was talking about with data gaps and time series data. And then some of the alerting, and then generation. So these are emails now that we can get where we can assess quality. When was the last time we had data, all this other stuff, so that some of our dredge operators and people managing the projects could know, hey, I haven't received data within, this is the last time I got data for this particular project. You guys go check something. Somebody set a call and do that. So these are now automated emails that go out. So it's not somebody having to sit down there, get in there in the morning. These are things that are always kind of churning and processing. So we can start to get data summaries and get it up to really decision makers to where if there's things that aren't happening, we're not getting data, or things need to be changed, they can actually have actionable data to act on them. Again, I had talked about before is we're actually migrating as well towards attaching within our geospatial functions, using the Uber H3 for all of our binning. Where that helps out with that is helps us get aggregates. We can do heat maps, we can do chloroplasts. There's all different kinds of things we can do with that. And so as the data comes in, we attach it with 3 different resolutions of data. What it gives us is a couple of ways for a couple of things. One, we could also shift over to eventually doing, let's say, a point and polygon on using just hex bin IDs. And then that's not a geospatial analysis. You're just, essentially it's an array, and how you can do the joins is just at scale can greatly improve performance. This is a H3 bin heat map with point data. And what I find interesting about this particular graphic is you don't see any of the polygons, any of the shape information, but you can clearly see where the ship channel is. You could also see where they dumped the material. So it starts to tell a story on its own just by taking the data, ingesting it and aggregating it, and then just putting it out there. We can really start to look at it and kind of see where some of these areas are into the distribution as you go over time within that. But like I said, you can see very clearly this is actually just south of Mobile. This is kind of heading out into the Gulf of Mexico. Geospatial analysis would be more in demand than ever. This is the who, what, why, where is going to be just as important as anything else. And as the things start to progress, GeoAI is really going to become that kind of next evolution, at least we believe, for AI. As a field in machine learning and geospatial data analysis intertwine, the benefits of geo-enrichment analysis will affect every industry and market in notable ways. Industry and market effects on geo-enrichment analysis. So identifying spatial patterns and trends, that's going to be hugely important moving into the future, as well as more opportunities for data segmentation. And then a lot of you may have heard the terms digital twin. That's essentially what this is one of the fundamental kind of truthful decision makers and data collection organizations that's going to help the Army Corps kind of develop their own version of a digital twin called the coastal digital twin, in terms of understanding where they're at that particular moment, but also how to plan future events. So if you know how things are going to be now, you can start to work on predictive and optimization strategies for how do you do it better. And then accurate predictions leading to better decision making. When you study a phenomenon over time, and in the context of a particular application, you begin to have a better understanding of why it happens, where and when it does, and that helps you better predict not only what will happen, but also when and where it will happen. It also can help you with scenarios, weather, all that. And we have some really great people working both out of the Mobile District and at ERDIC, the Army Research and Development Center out of Vicksburg. They're all tackling this problem. So, like I said, all of this is under development to help optimize, analyze, and improve the management of our nation's navigation systems. I do want to thank all the dedicated and hardworking people at the DQM program, the USACE Mobile District Spatial Data Branch, for letting me come up here and talk to you guys. Hopefully it took a boring subject and made it a little less boring. So, thank you.